Jan and Marika Holland out here at CU Boulder in the National Center for Atmospheric Research. And just to let you know, this work is actually currently in review in JGR Oceans. So hopefully I'm preaching to the choir here when I tell you that the Arctic is one of the fastest changing regions on the planet, but if you didn't know that, that is the case. So a lot of different things are happening here. We've got declining sea ice, river discharge has been increasing, and the Greenland ice sheet has been melting, for example. And so these, of course, are all just a very small set of subset of the many, many ways in which the Arctic, of course, has been changing, but they're all important to me because they actually impact how Arctic freshwater is sort of transported within the Arctic, and also how it kind of moves around and leaves the Arctic as well. And so this is a figure from Communique that basically is just kind of a schematic of the Arctic freshwater system, which sort of is basically kind of described by all of these different processes. So you've got sort of atmospheric transport of freshwater into the Arctic. You've got exchange between the atmosphere and the ocean through precipitation and evaporation. You've got riverine inputs, as well as ice and ocean transport sort of in and out of the various passageways within the Arctic. And of course, we care about this not only because it impacts the Arctic, but also because, for example, when you have transport through Fram Strait and the Canadian Arctic archipelago, this then, of course, impacts the North Atlantic. And then, from there, global overturning circulation. So these actually, all of these sort of impacts, understanding the impacts of freshwater, then we obviously want to understand why that's the case. So just a very, very quick overview there. But one of the things I really want to understand then is basically what is then going to happen to Arctic freshwater. So basically its storage and the fluxes through these various passageways as we move into the future. Okay, and so to do that today, I'm going to look at a bunch of, or a subset of CMIP6 models, and I'm going to characterize their Arctic freshwater storage and export during the end of the 20th and the 21st centuries to kind of put that future change in context. And so I'm going to be comparing ensembles from 7 different CMIP6 models in 3 different CMIP6 experiments. And so this is, again, this subset is chosen largely because we're looking for models that have at least 10 ensemble members in their historical simulation. So the first simulation is that historical simulation. It nominally runs from 1850 to 2015. But for my purposes, I'm mostly going to be looking at this 1980 to 2000 period to compare with observations. And then I'll be looking at 2 future forcing scenarios. So these are the shared socioeconomic pathways. These are kind of the RCP and the analogs for CMIP5, which are the RCPs. And this is SSP 1-2.6 and SSP 5-8.5. And so these 2 scenarios specifically are chosen because they kind of bracket the range of possible future forcing that we might see. And so the 2.6 is sort of a low radiative forcing scenario where you're going to have about 2.6 watt per meter squared radiative imbalance at the end of the 21st century. And in 5-8.5 is the kind of, I would like to burn my planet to the ground. I will not say business as usual, because apparently that's a no-no these days. But I want to burn everything to the ground sort of situation where you have 8.5 watts per meter squared radiative forcing at the end of the 21st century. And so when I'm looking at the end of the 21st century, typically I'm going to be looking at 2080 to 2100. For these 2 simulations. And so again, I'm using kind of ensembles of simulations instead of just one ensemble member and tons of different models, because there's a whole lot of models in CMIP6, largely because I also want to kind of start to look at the impacts of internal variability as well. And that will be a small part of this talk, but not most of it. So really quickly, volume. So freshwater storage is just basically the volume of freshwater in the Arctic. It's defined basically relative to a reference salinity. So you have this sort of salinity term here, and then you kind of integrate based on that. So you integrate over area, and then you integrate over depth, where Z is the depth of that SREF isohaline. So again, that's 34.8 is our reference salinity. So this is kind of a typical way in which we can define freshwater. It's not the only way. But we're doing that here. So we only go down to the SREF isohaline here just because we want to actually keep our storage values positive. Okay, and so storage is defined, the volume is defined as everything within these 4 straits over here on the right. So through the Bering Strait, Davis, Fram, and Barents Sea opening are defining my Arctic storage boundary. Now, export is computed similarly. You are computing your volume fluxes in and out of the Arctic relative to this sort of reference salinity. But in this case, we're actually integrating over all depth. And then, of course, you now have this velocity term here because you're basically looking at the fluxes through these passageways. And so now dA is just sort of a vertical face, whether it's going to be dx times dz or dy times dz. And so for the purposes of the export, we're also going to be looking at the export through the 4 main passages, as well as some of these straits in the Canadian Arctic archipelago, because these straits are now open in most of these models, or at least definitely in the 7 models that I'm showing today. So let's just jump right in here. So I just want to kind of give you an idea of what these models actually kind of look like in terms of their sea ice thickness and their freshwater column. And these are kind of 2 terms here that are going to be very closely related to the freshwater storage within these models. And so I am showing you 1980 to 2000 means, and they're the means of the ensemble. So they're ensemble means here for each of these 7 different models that I'm looking at. And so sea ice thickness is in the blue colors over here, and then freshwater column, which is basically just the integration of the freshwater only in depth space, so no multiplication over area to get the storage. And so these in the sea ice picture, again, we have sea ice thickness. And these, the colored lines here, we've got sea ice concentration contours. So the yellow line is the sea ice concentration contour. The 15% sea ice concentration contour, average 1980 to 2000 in each model. And then the orange line is the 2080 to 2100 sea ice concentration contour for SSP 1-2.6. And then the red is also 2080 to 2100 for SSP 5-8.5. So the whole idea of having the sea ice concentration contours overlaid is just to give you an idea of how much the sea ice is changing over that period. And it's quite a bit. So one thing I do want to focus on here is the major differences in sea ice thickness that you see across these models. You have some models that have a sort of relatively low sea ice thickness in the Arctic, like CNRM, CN6-1, and then very high sea ice thickness in UKESM. Same goes for freshwater. In this case, for the freshwater column over here on the bottom right in panel H is the PHC 3.0 climatology. So I commuted the freshwater column from PHC 3.0 as well, just so you have as the comparison. And again, when you kind of look across these models, you see a lot of differences, especially also compared to the climatology. So a lot of different things going on here, but at least largely, for the most part, you're getting some sort of increased freshwater storage within the Beaufort Gyre region of this. But again, huge differences. For example, CanESM sticks out like a sore thumb here, where you've got a really large freshwater column. And so then that, of course, like I said, directly then impacts the storage, the historical solid and liquid storage. And so this is the figure on the left here for all of these 7 different models. We've got solid storage in A and liquid in B. Do note that liquid is about a factor of 10 larger than the storage. And so this is again for historical. So we're looking at that 1980 to 2000 average period. But in this case, I am now showing you the spread of the individual ensemble members in each of these models. The dashed line is observations. And then these either gray or blue shading is kind of the error on those observations. So gray is actually the errors that are reported in papers, and then blue is an estimated error if there is no error reported. And so in the case of the storage, what you see is, again, the models kind of don't agree super well on what the storage is. You only have a couple models getting fairly close to observations. And then, for example, the solid storage is really high in UKESM. Liquid storage, same kind of story, some significant variation across the models. And then this really high liquid storage in CanESM, which we know is considerably fresher than the rest of these models. You can also look at the fluxes. And so in this case, for my fluxes, anytime I think about this, the sign convention is always going to be a positive flux is a freshwater flux into the Arctic, and a negative is a freshwater flux out of the Arctic. So looking at our solid fluxes here, again, the sort of main takeaway from all of these fluxes is that the models have a really wide disparities in what they're saying the actual historical fluxes are. There's only a couple of models typically for any given strait that get fairly close to what the observations are. Again, observations are also 1980 to 2000, but we know that those are super sparse as well. But a lot of sort of different variations among the models, and some interesting things happening within their actual spreads as well. Same thing for the liquid storage. where again, there's only a few cases where everybody either kind of underestimates the liquid storage like they do in Barrow Strait. Again, and kind of not a lot of model agreement on sort of and sometimes disagreement on even sometimes the sign of these fluxes. But for example, in the Barents Sea, most models are getting somewhat close to what this storage would be. So again, a lot of sort of major sort of intramodel spread as well as intermodel spread within these 7 different models. So looking into the future then, the future storage, basically you see a major decline in the solid freshwater storage and an increase in the liquid freshwater storage. And that's not really surprising because largely your sea ice is just disappearing over time. And so now on the left, I've got the ensemble mean freshwater storage for these different time periods down here. So the historical, and that is in gray. SSP 5-8.5 is always going to be in the goldenrod, and 1-2.6 is going to be in the blue. Kind of what you see from the solid storage is basically compared to the end of the 21st century to the beginning, or the end of the 20th century, major declines in the solid storage. And then overall, everybody says an increase in the liquid storage that's typically larger for SSP 5-8.5 than it is for SSP 1-2.6. And so how this then evolves over time, how do we go from historical to these future scenarios? This is just a time series of the multi-model mean now. So your eyes don't go a little too crazy having to compare across all these different models. And so the multi-model mean here is the mean of the ensemble means of each of these 7 different models. And so that's to kind of combat some of the fact that some of these models have different numbers of ensemble members in them. So again, largely what you see is this decline in the solid storage that's a little bit less for 1-2.6 than it is for 5-8.5, and then sort of an increase in the liquid storage. And just for the record, these envelopes are showing the max or the minimum value that any of the seven ensemble means achieves, and it's not a 95% confidence interval. So it's a little bit broader than that. So looking at the future solid freshwater fluxes, the solid fluxes again kind of tell this story of declining sea ice everywhere, where kind of across the board, and most of these, in all of these models, sometimes you have sort of differences in sign, but largely you're getting declines in solid freshwater fluxes because you're getting rid of your ice, and those are typically stronger in SSP 5-8.5 than they are in SSP 1-2.6. So the liquid fluxes kind of tell you a slightly different story though. Oh, sorry, we're not doing that yet. So this is the kind of the time series of the solid freshwater fluxes first. And again, those are kind of largely saying the same thing. Everybody's kind of going towards 0 over time, although there are, at least in Fram Strait and maybe in Davis Strait, some indication that there actually are some differences between these 2 model scenarios, but not very strong just because there's just overall a major sea ice decline. Liquid fluxes are a little more complicated. We see some increased freshwater export for the most part in the Barrow, the Nares, and the Fram Straits, and Davis Strait as well. A couple of interesting things that are happening here in the Bering Strait, for example, though. You've got some models showing some increases in these scenarios, some showing some decreases, but there's not a lot of change, at least looking in each model from the historical to the future scenarios in Bering Strait. And then in the Barents Sea, for example, the Barents Sea opening, you actually get this flux sign reversal. So you're going from having sort of a negative freshwater flux, so a flux of freshwater out of the Arctic, to over time having a flux of freshwater into the Arctic. So real quickly, again, looking at the time series then of these multi-model means, you see that relatively stable then Bering Strait freshwater flux in both of these sort of future forcing scenarios, and then sort of declines in the fluxes in Barrow and Davis and Nares as well. And then in the Barents Sea, you actually see this sort of increase in the fluxes. And to some degree, there actually may be some difference between these 2 scenarios by the end of the 21st century. So to kind of understand then why we can get flux sign changes, we need to kind of go back to our understanding, our sort of definition of the transport itself or the export. So these are the volume fluxes in and out of the Arctic. If you notice, there are actually 2 different ways in which you can get a sign change, you can actually impact the salinity and you can impact the velocity, okay? And so if we want to kind of figure out which of these things matters for the actual flux changes, we decompose our freshwater fluxes to get these separate time-varying salinity and volume contributions. So the time means are going to be relative to 2000 to 2100 means. That's what your S bar and U bar are. And then your S prime and U prime are going to be those the anomalies relative to those means. And so I'm not going to kind of look at all four terms that you can get from this. Mostly I'm just going to be looking at U bar S prime and S bar U prime, just to kind of get at, again, these time varying salinity and volume pieces. So real quickly, here is our freshwater flux originally. And then what we have on the right then are the decompositions. So this is now the contribution to the volume flux in purple, or the volume flux contribution is in purple. So that's the contribution to the freshwater flux. And then in green are the contributions to the salt fluxes. And then the darker colors are 1-2.6 and the lighter colors are 5-8.5. And so I'm not going to go through all of these about why things occur the way they do, because this is actually a fairly complicated figure when you start to kind of unpack things, but I'll talk about a couple. So in Bering Strait, for example, what you see is that the contributions of the salinity and the volume fluxes over time are compensating. And so even though you actually have a reduction in the volume fluxes in this strait, at least in the multi-model mean, you actually have you have a freshening as well. And so that is going to then those two things compensate. And so your freshwater flux stays relatively the same. Now in the Barents Sea, for example, the volume flux contribution, which is that purple color again, is never really all that big. Instead, it's really a salinity driven thing. And so that way, what ends up happening is that you're actually, even though you have, you don't really change the sort of inflowing waters, if you will, it's rather that you're changing the salinity of those. And so you're freshening that over time. And so then the Barents Sea actually becomes a source of fresh water for the Arctic Ocean. And then real quickly, one thing I do want to point out, kind of shooting myself in the foot here a little bit, is that the multi-model means really hide a lot of major model differences. And this is particularly true in the straits west of Greenland. Now I'm actually just showing pure volume flux, so no salinity involved in this at all. And if you look across these different models, and the Narrows Barrow and the Davis Straits, you start to realize that your averages are kind of an average over a lot of different behaviors that are occurring. And so that's kind of something we take into account and discuss in my paper in more detail. So here are my conclusions, and I'm just going to leave that there for you. So thank you. Questions?
Thank you, Hannah. We can take a quick question if somebody has a question right now, or we can save to the end after Lars presented his talk. I don't see any question right now, so how about we hold to the end, then ask question together. Lars, are you ready?
I'm here now. Yeah, sorry for being a bit late. It's evening time in Norway, and I incidentally got the 1 hour wrong, but I'm ready to go here now. So thank you for inviting me. I'm Lars Medsrud from the University in Bergen. I'll start sharing my screen, and I will present. Maybe my task is easier than the one Hannah just did, because she did all the straits. I'm just going to look at Frem Strait, but I think you noticed that from Hannah's figures, Frem Strait is really the major export area of both solid sea ice and also fresh water from the Arctic. So it's the main gate. And what I'm not going to look into the future, I will just present changes that have occurred. So addressing kind of the same questions, but over the observed period. So I'll base this largely on a paper that's a few years old now, with co-authors listed here, but it's in the cryosphere, but I'll add a few more things as we go, right? So I'll talk about the Frem Strait sea ice export mostly, what it is, why it matters, a little bit of controversies, and then give us a summary. So I think this is the uncontroversial things comes first. So I think this is going to be consistent with the numbers that Hannah showed as well. Roughly 10% of the area inside the central Arctic basin here is exported every year, right? So that area is roughly 8 million square kilometers. And then the annual export is, close to 1 million, so 880,000. This is our numbers for the 1935 to 2013 period. So if you just care about the summer area, then this is 20% of the ice cover, right? So anyway, it's a big flux, and I think the most of the models get this fairly correct. I think most export, at least those we've checked before, actually over-export. Maybe you can comment on that, Hannah. Did you look at, but you had all sorts of variability in your plots, but at least they get the correct magnitude, usually the models. Yeah, so this area export has a high seasonal cycle. It's a lot stronger in the winter, and this is because we are blowing the winds much harder, right? So this is the average winter speed that we found, and this is the average summer speed. So 3 times faster ice velocities in the winter. So this is based on the SAR imagery that we had access to from 2004 and 2013. And then what we did is to do the seasonal cycle. This is consistent with what has been done afterwards as well. But you see velocities between around about 15 centimeters per second in the winter, and then around about 5 centimeters per second in the summer. And this is consistent with other estimates as well. And we did this based on SAR tracking. So we claim that this is slightly or a little more accurate than passive microwave. I'll show you some examples, but this is actually done manually by a person now retired at the Nansen Center called Kjell Kloster. So he did this by looking at every image and then finding these arrows. So he recognizes features and he does the tracking manually. And we actually checked that this is better than, you can do this automatically now by feature recognizing software, but the human eye is still better than those software packages. So what we did was to produce the regression towards geostrophic wind, and we binned the averages, and then we found monthly means. And we used those backwards in time towards pressure. So we found that, we don't really have, we go back to this map, we have the SAR data from 2004 to 2013, and we have pressure observations from these points. So we want to understand how this varied in time, since we started measuring pressure, and this is what we get then. So this is how we produce the long-term mean of 880,000 square kilometers. That's the annual values here. You see the black line, and then we divided it in winter and what we call spring. So we say that spring starts in March and lasts until August. So there's just two seasons in the Arctic, according to this paper. But the point is that there's larger trends, or we found larger trends from the 70s until 2015. And we claim that this is a part of the explanation for why we have had the September variability that we've seen. So if you draw the long-term trend, there's none, right? So we initially, in the first paper some years ago, we made a big note of this, that the overall is a trend, but if you go back to the 1930s, 40s, 50s, there is really no trend. So this is just atmospheric variability, I think. So why does this matter? I think what I've been doing the last year is to look at the heat budget of these basins in the north here. So this is just submitted to Reviews of Geophysics, and we're trying to look at the cooling of the ocean, so the heat loss of these basins. And if you do that, then you will recognize that the Fram Strait sea ice export is actually a lot of heat as well. So Hannah talked about fresh water, which is clearly important, but this ice export is you know, almost at the same magnitude as the total heat loss inside this area, which I would like to call the Polar Sea, actually, because I want to call the whole thing here for the Arctic Ocean. So we make a point that the Nordic Seas is a part of the Arctic Ocean, and this is actually consistent with the International Hydrologic Office. This is the Barents Sea, which also has a large heat loss. The Nordic Seas dominates the heat loss if you look at this area, and surprisingly, maybe there's a fairly small heat loss here. And this is because A, you're growing ice, and B, so when you're growing ice, the heat gets to the atmosphere, but you're not really cooling the ocean, right? The cooling only occurs as that sea ice is melting. And if you melt and freeze over the year inside the same area, there's no average heat loss. So this is simulations using the NORSM over the last 100 years. And we find some large trends, which I won't go into here, but just note that the ice export is also a lot of heat. So you're cooling the Nordic seas, and the heat is transferred to the Arctic atmosphere up here, but it's cooling the Nordic seas. Okay, and then also, as it clearly Hannah showed, that the freshwater budget is important, or the Fram Strait ice export is important for the freshwater budget. So this is nice paper from Isabella Lebras, now in Woods Hole, but she had this nice question: how much Arctic freshwater participates in the subpolar overturning? And then we look at this is the OSNAP array here, right? This is Fram Strait, this is the Barents Sea opening. And then the main result of the paper, I think, is that, you know, about half the fresh water that comes in here gets into what we call overturning, right? So this is the inflow, the AMOC that Wilbert works a lot with, you know, the warm water coming in the surface, getting denser and flowing south as dense water across this strait here. A lot of it also participates in the estuarine circulation, which is the other 50% then. So that's part of the circulation that a lot of people forget, but it's an important part. And you know, the main point is that if fresh water comes in at this gate, just sticks along the coast and exits on the south tip of Greenland, it doesn't really matter, or you know, it matters, but it just flows through, so it doesn't participate in this. And then this is the sea ice part of it, right? So we looked at the freshwater forcing in this area, and sea ice is actually the major freshwater forcing if you just look at the surface fluxes in this area. So that's, if you add 41 and 30, you get to 71, and this is the total roughly. So 110 millisverdrups is what is coming to the Nordic seas and the extended Nordic seas then as we go to the OSNAP array. And the ice export in the Fram Strait is a big part of that, right? So Greenland is only 10 millisverdrups. The surface rain is 11 millisverdrups, and the river is 13 millisverdrups. But clearly the Fram Strait ice export is the major part of the freshwater forcing for this area. So it matters for that reason.
Lars, we lost your audio a little bit.
Oh, okay.
Okay, good now. Thanks.
I will talk slowly. So for the freshwater export, you also want to know the thickness, right? So there's good work being done at the Norwegian Polar Institute with Gunnar Spreen, where he looks at the ice area export that we looked at, but then he also adds the thickness. And clearly, as Hannah pointed out, there's a thinning going on, and this has been going on since the 1990s when they started measuring the thickness. So overall, the volume export is going down because the ice is getting thinner. And they use a variety of area export to estimate this, but it's consistent with different estimates of ice export. So the numbers that they use are consistent with our values, right? So if you have about 1,000 this is close to 1 million square kilometers, sea ice thickness 2.5 meter, then you get a volume export around 2,500 cubic kilometers per year, right? And this is what the values you see here. So, yeah. So then we looked at the difference between the values that we produced since the 1930s, but then this model is a fairly high resolution RV model of the sea ice and the ocean. And we noted here the area of influence. So if you export Framstrait sea ice here, then this is the area that sort of feels it, right? So you can expect that anomalies in export influences a fairly large part of the ice upstream. And these are the different trends. So if you, for example, look at the NSIDC passive microwave product, it has a larger trend than what we found. And we suspect, I think, that the early NSIDC estimates are biased low. So you see over time, they agree more with what we found. And yeah, so there's a bit of discussion about this trend that we found, but clearly if you look at NSIDC data, it's larger than what we state. So then we make a claim that the Arctic September sea ice extent is it's influenced by the Framstrait export. And we actually suggested that you could use this as like a prediction of it. So this is just the September ice extent values over time back to the 1930s, thanks to the Walsh data set. And you see that, it really only started declining in the 80s, right? Until that, there's actually a small positive trend here from the 1930s until 1950s. Then we found fairly, or at least somewhat high correlations between the ice export and the September extent, right? So for example, in 2012, everybody remembers that minimum. And also then in 2006, both the ice export was high and you had a small September ice cover. So we think this should play a role. And if you just look at the correlation, then you can say that 53% of the variance is explained since 2004 with our data. So I know that it's a little bit controversial, and this is the last point then, but I think this could be checked, and people have partly done it, but the mechanism is simple, right? If you have an anomaly in export, so you just push more ice out in the summer, clearly you have solar forcing, that heat is gonna get into the ocean, and that's gonna melt some more sea ice, and that's in the summer. I think anything you do to the sea ice will be you will have the ice albedo feedback, and an initial ice export anomaly will be amplified by the ice albedo feedback, basically. So that's what I plan to go through. Just a summary here. Seasonality and export is explained by winds and currents. We did some work to include currents as well. The annual export value, there is a long-term value. So I don't know if this is what you compared with, but this is the area export then, right? We don't have thickness data before the 1990s. There was some events with very high export in late years and around that September minimum. So we hold that this had an influence. There is lower variability in export during winter, even though the export is higher. And there is a fairly large trend in spring ice export since the 70s then. But it's only like 10% of the anomalies in the loss. So you do need something to amplify it. And export influences Nordic and Arctic heat budget. It also influences the freshwater budgets, right? And there's a bit of controversy around this September and also the trends since the 1970s then. So I know that some of our results is is different from, for example, what Ron Kwok finds. He doesn't see this increase, but I think it can be resolved if we want to. Okay, that's what I plan to show. Hope I didn't use too much time. I have more slides, but I think that's good.
Thank you, Lars. Perfect timing. You get us back on track. So yeah, I saw there very active discussions between Sultan and Hannah in the chat box.
I didn't.
I mean, we can some new questions if anybody has them, or Hannah, you can give like a brief summary of what you guys talking about. But first, let's see if you have any new questions. You can just turn on your speaker. You have a question to ask, or feel free to raise your hand, whichever way you feel like. If not, I have a question, Lars. You mentioned that about 50% of the substrate export, if I remember correctly, kind of involved in the related to AMOC variability. So, but what's the impact of this amount export in AMOC exactly? Have you quantified the relationship between the frame state export and AMOC into any variability, for example?
So what Isabella did, and I was a co-author, she made up the average over that, so she did an inverse model based on observations to just try to understand where the fresh water really goes, right? So we didn't use freshwater fluxes because it's dependent on this SREF that Hannah also presented. So to some extent, it's not really a good, it's, if you want to look at the, proper salinity budgets, you really should look at the salinity or the salt fluxes. And this is what she did because she had the observations, and then, but then you need an inverse model, and volume anomalies become very important, right? So we just did that to get a good feeling for the average situation over the last decade or so. So we didn't look at anomalies, and but one point, I showed how the Fram Strait sea ice export is distributed, right? So we just had to assume that the stuff that melts on the shelf really stays in the East Greenland current, and the ice that melts in the, off the shelf participates in this, the overturning, really. So the ocean doesn't feel the difference between melting sea ice and precipitation, obviously, right?
Mm-hmm. Yeah. Thank you. I saw a question from David Bailey. In terms of streets, West or Greenland, how many CMA models only have one street through the CAA? Do any have more than two? I guess the question is for Hannah.
Yeah, so I put that in the chat. The ones that I looked at here all had two. And don't worry, that's okay. That's okay. Don't worry about it. I can answer it here too. So the ones I looked at all had two. I cannot speak for the whole of CMIV6. So there are like 50 models. and so I don't know who has one versus more than, or potentially more than two at all, Dave. But at least the ones I looked at, I know had two at least, so.
Thank you.
Did you look at the freshwater fluxes or just the volume fluxes through the Canadian archipelago? Is that kind of constrained between the models? I mean, you would assume that the number of straits would control the volume fluxes.
Yeah, I'm sure that they do. So I did look at freshwater fluxes through there, but I also just looked specifically at the volume fluxes because I didn't, in the end, kind of doing this salinity you know, reference salinity thing gets a little bit weird when you're trying to keep track of salinity fluxes. And so it was kind of, it was not really, I don't think really feasible to keep track of the salt separately in the models. So like what I did was I wanted to kind of compare to observations and kind of just keep everything as consistent as possible with what's going on. But so those volume fluxes we did look at separately, because I was like, well, at least this I can tell whether or not the volume is, you know, the velocities are changing, right? It's like the very clearest picture of that. And so my guess is that, yes, it is highly tied to which straits are open. I would not be surprised, and what can actually go through there, just because it depends on the size of your strait as well. And so I don't know if that's, depending on the model, if that's tuned or not, that you can get into a whole hairy area. But I imagine that, you know, it's possible that, yeah, having more straits open will certainly, and depending on what they do with the one strait situation, will certainly impact that. But my guess is that in some models, if you had only one strait open, they may actually make the strait either larger or, you know, less deep or whatever it is to account for some of those differences in fluxes. But okay, it really varies.
Thank you, Hannah. I thought to have the reading, Wilbert first, then David. Wilbert.
Yeah, excellent talks, Lars and Hannah. That was really, really insightful. Thank you very much for that. I got a couple of questions for Lars, but let me start with just one. And that is that I wonder if you could give us a little bit more insight about how do you calculate the heat flux associated with sea ice export? Because I think you diagnosed a kind of a southward heat flux through Frem Strait, but then you said it was cooling the Nordic seas. So is that a kind of a negative heat flux that goes north when the sea ice goes south, or how do you define the heat flux associated with sea ice export?
Yeah, so this is an ice ocean model, right? So it this is it's a 100-year mean, and it's basically the volume of sea ice that's exported. So I know it's a little bit too high compared to my own observations, but it's very close to, or quite close to. So it's then just simply the energy that's needed to melt this ice, right? So it's the volume flux times the latent heat of freezing. And maybe the density is in there, but it's a fairly simple thing to calculate. And this is just the long-term mean. So it's just proportional to the ice volume export.
So okay, so you're saying it's mostly a kind of a latent heat flux that is represented by that. Yeah.
So the Nordics, I mean, so all of this sea ice melting in the Nordic seas is going to cool the Nordic seas, right? All of that heat is taken out. So I mean, this is an ocean-centric view of the heat fluxes, right? If you might be a meteorologist would say that this heat goes to the atmosphere, right? So the atmosphere above the green area gets the 17 terawatts, but the ocean gets the cooling. So if you care about, so we cared about Atlantic heat lost, and then much of, so we know that the warm Atlantic water directly melts sea ice in this area, both north of Svalbard, but also in the Greenland Sea you have. So some of the inflow Atlantic heat is actually directly melting sea ice. It's not lost to the atmosphere.
Yeah. Right. To think a little bit more about that. All right, but thank you. David, do you want to ask a question?
Mm-hmm.
Sure. Yeah, just following on from the various passageways through the Canadian Arctic archipelago, I think Hannah highlighted already that, even though there may only be two, they adjust the volume, so that it gives you roughly the right amount of volume flux. But it's always interesting to look at the solid versus liquid part of that to see if it matters or whatever. But the reason I had asked about how many of the CMIT models do this, because sometimes even though they sort of tune these straits, the details kind of matter in how you know, how you do that exactly. But yeah. So, and then Lars, I was interested too in your experiment. So you ran with this 20th century reanalysis. Have you looked at other ice ocean force experiments with like JRA and SEP-NCAR? I know those are shorter, but does that sort of change the distribution?
Of the heating or the heat loss, you mean?
Yeah.
Yeah. So, well, so we looked, the JRA forcing was the one we used for the freshwater thing. So we looked there, but there's but you know, basically no, because we in this thing that we just submitted to is kind of a review, and I thought there's quite large changes that we have seen. For example, in the inflow of Atlantic water west of Norway, right? That was our motivation. But then I didn't know of estimates over the last century. So, and I think my interest in this grew from looking at the Fram Strait export, because I see it. So you see a big trend from the 1970s until the 2000. And then I wanted to know, okay, is this really unique over the last century or not? And then it's only the 20th century reanalysis you can get, or there's also an era in 20th century version that we did not look into because it's more recent, and our Norwegian Earth system model has not been set up for that. But it's all forced by the same pressure observations, right? So I'm not expecting very large changes, but it would be worth to check, certainly.
And just for the one person on the phone, if you click *9, you can raise your hand or unmute yourself *6 if you have a question.
Thank you, Meredith. Yeah, any more questions? I saw Wilbert, your hand is raised. Do you have any more questions? Or Mitch, Buruk, please.
Yeah, I had a quick question for Hannah. So can you hear me by the way?
Yes.
Okay, great. So I was interested in this this column integrated freshwater content you were showing, and you were comparing the CMIP6 models, I believe, to the PHC climatology. And it seemed like in terms of that metric, most CMIP6 models did pretty well, with the exception of CAN-ESM5, I guess. And I was wondering about the vertical structure of the freshwater content. So like, are the models getting the right Arctic halicline? Is the freshwater in the right vertical locations? Or like, I could imagine it getting sort of the right net freshwater budget in a large scale sense, correct, but having the wrong vertical distribution. So I was wondering if you had checked that at all in CMIP6.
I have not looked specifically at the vertical structure, Mitch, but if I had to hazard a guess, I would say that they probably don't do all of that super well, if I know anything about working with models after this many years. But I can't speak to specifically what about them would be an issue. I think most of them have their fresher water toward the top, and then your more saline water trapped in the very deep parts of the ocean. But in sort of in between, thinking about actual like Atlantic inflow versus Pacific inflow, that I can't really tell you anything beyond that, beyond this sort of integrated aspect of that. But I suspect it probably leads to some of the patterns that we do and differences that we do see.
Right. Part of my motivation is that in the GFDL models, we've had this issue with too much vertical mixing, and we have these very persistent sea surface salinity biases in the Arctic. So we're kind of moving too much salt water up. So we have the right amount of fresh water probably, but it's not in the right spot kind of. But I was wondering how ubiquitous that was across models.
Oh, I gotcha. Yeah, I don't know. I can definitely look for you though, if you'd like me to do that.
I would love to if you have time, but no pressure.
Yeah. No, I don't, but that doesn't matter. I'll see. I'll dig around and see what I can take a look at though. Okay.
Thanks, Hannah.
Yeah, of course.
Thank you, yeah, great discussions. Thanks to speakers and all the participants. We have 3 minutes left. I think I asked everybody to type in the chat box any update you may have, and also for the next meeting, Wilbert type in there. We plan to have a meeting with the glacial team to discuss tracking of Greenland freshwater in the Nordic seas, and we will keep you updated. I think 2 more minutes, we can probably take 1 or 2 more quick questions. I saw Bjorn Erlingson, do you have any questions? I'll turn your video on. No, okay. Anybody have any update to share or any last minute questions?
I had a question, Anna, so I think it's a nice, I think your main result is that the Arctic sea ice melts.
Yeah.
Is not there anymore, right? So there's a lot, and the freshwater fluxes and the storage did not change that much. So basically so what happens to all of that freshwater in the models? I mean, it leaves the Arctic basically?
I'm not sure. I mean, I think a lot of the sea ice at some point is actually staying and just melting within the Arctic, but I can't be 100% sure on that because at some point the fluxes themselves are actually declining. It just doesn't impact the liquid freshwater that much because the volume of the ocean is just so much bigger than the volume of the sea ice. And so some of the changes in the liquid freshwater are actually due to riverine and P-E inputs. I just didn't show a lot of that or any of that today. So that is my sense, is that actually it's just kind of a reduced sort of, you're just not forming as much sea ice over time, but that's like in a very long-term view. In terms of sort of beginning changes, you can imagine you have times where you actually have increased sort of export as you are able to move ice more freely, but then depending on where you move it, where it actually melts will differ as well. So I can't speak to exactly where that is, but I think at least part of the storage increase actually has to do with the sea ice just melting within the Arctic and never making it out at all.
Yeah, and it doesn't show up in your budget if you grow ice and you melt it within the...
Yeah, we don't think about the ice ocean exchange. We just kind of treat them as like separate pieces and don't really do an actual budget for that reason. We just say, okay, here's what's changing and this is most likely why.
Okay.
Yeah, I thought they would have another question. I'm curious about this too, actually. Does the atmosphere resolution make a difference?
Probably. They do definitely have different atmospheric resolutions that we're looking at as well, Dave. And so that will obviously depend on sort of the wind-driven impacts, especially on the sea ice. But again, it wasn't something that I particularly looked at in terms of what the impacts would be. But I can imagine that it will definitely affect sort of fluxes, especially in and out of these passageways and sort of how you can then impact the upper ocean as well. So.
Yeah, also I was amazed to see the widespread of the model results among different class of models. And before like more observation available for us to kind of have better kind of validation, etc. Yeah, wonder what's the strategy for kind of narrow down this kind of uncertainty that spread. But that's
I didn't spend a lot of time looking at like what the mechanisms were behind these things, and that's just like a whole nother really interesting area. Yeah. But it's just more like here's an assessment of just this very small class subset of these models. So.
Yeah, very interesting. Yeah, very informative. Thank you both, Lars and Hannah, for your excellent presentations, and thank you all for your participation and discussion. And thanks, Betsy, for sharing the update in the chat box. And thank you very much. It's a great meeting, and hope to see you next time. Thank you.
Thank you.
Great. Thanks. Bye-bye.
Bye.